Okay, and then I start to introduce you, and you can start to quite a few people online now. Hello, everyone. Hopefully you can see me, but if not, that's fine. Yeah, so yeah, we'll be very happy to host a visit of Dr. Juan Gómez-Luna, who is now a senior researcher and lecturer at the separate research group at ETH. He received a bachelor and master degree in telecommunication engineering from the University of Sevilla, Spain, in 2021, and a PhD in computer science from the University of Cordoba in 2012. So between 2005 to 2017, he was a faculty member of the University of Cordoba. His research interests are focused on the processing memory system, heterogeneous computing, and hardware and software acceleration of medical imaging and bioinformatics. He's the lead author of the PRIM, and also the first publicly available benchmark field for the real world processing in-memory in-memory architecture, and the CHI, a benchmark field for the heterogeneous system with GPU, CPU, and MPT. So let's welcome Juan to give us this talk. Please.
Thank you for the introduction, and thank you for attending this this talk, both on site and in Zoom. It's my pleasure to be here and introduce and present this work, Understanding a Modern Processing in Memory Architecture, Benchmarking and Experimental Analysis. This is some research work that we have been doing for the last 2 or 3 years, and I think it's processing, working with a real world processing in memory architecture is something really exciting for us, and we are pretty happy to be able to explain you what we are doing. So let's start with a little bit of motivation about data movement, because that's a main reason why we need processing in memory systems. Data movement in computing systems is consuming most of the energy and the execution cycles. For some example numbers here, you can see in the slide that the total system energy for consumer applications, scientific applications, and mobile applications is spent on data movement, something between 35% and 62% according to previous works. And this is because in computing systems, there are many different components like CPUs, GPUs, accelerators, cache hierarchy, and the external of chip DRAM. And there is a lot of communication between all these different components, a lot of data movement. So one way to alleviate this data movement is to make compute systems more data-centric, and that basically embedding or including processing in memory capabilities that allow us to compute where the data resides, where it makes sense. This work is about the UPMEM PIM architecture that, as far as we know, is the first publicly available real architecture. It's fabricated by a French company, a French startup called UPMEM, and it's based on DDR4 DIMMs. Inside each of the DRAM chips, as you will see, there are not only memory arrays, but also small processors that are called DRAM processing units or DPUs. But before we go into the details about this architecture, let me start with an executive summary. As I mentioned, data movement between the memory and the storage units is a major contributor to the execution time and energy consumption, and processing in memory can alleviate this data movement. It's being explored for many, many years, for more than 50 years for sure, but only now we start to see the first real-world devices. In the case of UPMEM, as I mentioned earlier, these are DDR4 chips embedding in order multi-threaded DRAM processing units or DPUs. In this work, we do an introduction to the UPMEM programming model and PIM architecture. We have done a micro-benchmark-based characterization of the DPUs and a benchmarking and workload suitability study. Main contributions of our work are the comprehensive characterization and analysis of the UPMEM PIM architecture and a benchmark suite that is called PRIM, consisting of 16 workloads that are memory bound in conventional processor-centric systems like CPUs or GPUs. We have characterized these workloads with the strong and weak scaling experiments and have compared them, their PIM versions, to the state-of-the-art CPU and GPU versions. Takeaways of our work are the workload characteristics for pin suitability, programming recommendations, and suggestions and hints for hardware and architecture designers of future pin systems, and the PRIM benchmark suite. We have published this paper in the IEEE Access Journal, but there are also a couple of versions of the paper in archive. The first one is as a short version, just summarizing the most important takeaways of the work. And there is a longer version that is, as you see, you can find the link there. The repository is also available. You can find the link at the bottom of this slide. So in this presentation and also in the paper, you can find many of these boxes with programming recommendations, key observations, and key takeaways. I'm just showing these for you to, first of all, recognize the colors, and then to understand the reason why you will see that sometimes some of the numbers are not in order, or some of the observations might be missing. But it's just because I wanted to keep them with the same numbering in the paper and in this presentation. By the way, feel free to stop me anytime whenever you have questions, either here in the room or in Zoom, because I think this can be more interesting if we have a little bit of discussion as we make progress in the presentation. Okay, so this is the outline. First, I will start talking about the execution model that this PIN system uses, and I will give an overview of the admin-based PIN system. This architecture, or this PIM system, follows what we call the accelerator model. In this case, admin DIMMs coexist with conventional DIMMs, and the integration of admin DIMMs is like an external accelerator or a loosely coupled accelerator, where we need to explicitly move data between the main processor and the accelerator, and then explicitly launch the execution onto the admin processors, onto the DPUs. In some sense, this is similar to GPU computing. We first move data to the accelerator, then launch the execution on the accelerator, and then we retrieve the results back to the main memory of the CPU. Regarding the system organization, as I said, in the same system, we have admin DIMMs, but we also have regular DDR4 DIMMs that still work as the standard main memory. As you see, we have the main memory, we have the host processor, and we have the PIM-enabled memory. We can take a closer look at the PIM-enabled memory. Each of the DIMMs in the most recent generation consists of 16 chips, 2 ranks of 8 chips, and inside each of the chips, there are 8 64 megabyte banks, DRAM banks, that are called main RAM or MRAM, and 8 DRAM processing units or DPUs. So in total, we have 64 DPUs per rank and 128 per DIMM. We will go later into the details of the internals of the PIN chip. But before that, let me show you the system that we used in our analysis, in our study. Is an admin-based PIN system with 20 admin DIMMs, each of them with 16 chips, as I said, and a dual socket CPU. So in total, there are more than 2,500 DPUs and 160 gigabytes of PIM-enabled memory. And this is a picture of the admin system with the dual socket CPU, some DRAM DIMMs, and the PIM-enabled DIMMs. And in our study, we also use a smaller system. In this case, is with 640 DPUs. That was the first system that we had access to. In total, 640 DPUs and 40 gigabytes of PIM-enabled memory. Let's start with a little bit of explaining how to program this system and how to partition workload over the available PIM cores or DPUs. If we think about most basic programming examples that we can think about, is a vector addition. In this case, we are doing the element-wise addition of 2 vectors. The way that we distribute the workload over the PIM cores in this system is by partitioning the input arrays equally over the DPUs, and then sending from the main memory to the MRAM banks, the DRAM banks of each of these DPUs, sending them the input arrays. So this part of the computation could be for DPU 0, DPU 1, DPU 2, and DPU 3. And then inside each of the DPUs, because as you will see, these are fine-grained multi-threaded processors, we have multiple threads running. So each of them will take its part of the chunk that was assigned to each DPU. So this is for tasklet 0, tasklet 1, and similar thing on the rest of the DPUs. As I said, we need to explicitly move data between the main memory and the PIM-enabled memory, and vice versa. So this is what we call CPU to DPU transfers and DPU to CPU transfers. And the SDK provides different ways of doing these transfers. The first one is serial CPU, DPU, or DPU, CPU transfers, where we target a single DPU or a single MRAM bank. The second one is CPU, DPU, or DPU, CPU parallel transfers, where we target multiple DPUs or multiple MRAM banks. And in this case, we might be transferring different buffers to the different MRAM banks, but these transfers need to be of the same size. And finally, there are broadcast CPU, DPU transfers, where multiple DPUs will receive a single transfer. Understanding these and how to do these data transfers and how fast they are is something that we did in our work. And it's important because they are used for inter-DPU communication. There is no direct communication channel between DPUs. So even if you want to communicate data between two DPUs that are in the same chip or in the same DIMM, you will have to move the data back to the main memory and then again from the main memory to the specific MRAM bank. So all these inter-DPU communication can be very costly. Obviously, in some of the workloads that can be a huge overhead. In some other workloads, the cost will be amortized by computation, so it won't be so terrible. There are different example communication patterns where this inter-DPU synchronization or communication is needed. For example, merging partial results to obtain a final result. This only requires DPU to CPU transfers, or redistributing intermediate results for further computation. The same as, for example, if you think about graph processing algorithms where they are iterative, we generate one frontier after each iteration, and we need to redistribute the frontier, the work over the multiple DPUs in order to continue with the execution of the next iteration. In the paper, as I said, we evaluated how fast are these data transfers. I don't have the results here. They are as backup slides if you want to take a look later, but basically we used here a couple of micro benchmarks targeting a single DPU for different transfer sizes or a rank of DPUs. And in our preliminary experiments with more than one rank, what we observed is that we can exploit channel level parallelism. So basically the bandwidth, maximum bandwidth here is limited by the bandwidth of the DDR4 memory. And as I said, these transfers might be costly in some cases, but hopefully the cost will be amortized with the computation that is going to run on the memory side, on the DPUs. Let's go into more details about the DRAM processing unit. We created here several micro benchmarks to evaluate arithmetic throughput and also the bandwidth to the different memories that the DPUs have access to. The DRAM processing unit is inside the PIN chip. In the PIN chip, there are a couple of interfaces, control and status interface and DDR4 interface. These are for the host to access the PIN chip. And then inside the PIN chip, we also have 8 MRAM banks or 64 megabyte DRAM banks. And we access to these MRAM banks through the DPU. The pipeline will access to this bank through this DMA engine. We use the DMA engine to either move instructions to the instruction memory, which is of size 24 kilobytes, or to the scratch pad called WRAM. It's not a cache, it's a software managed cache of size 64 kilobytes, and where we store input and output operands. And the left-hand side, you can see the pipeline. In total, the pipeline has 14 stages. It's an in-order pipeline. In the DPUs that we use for this analysis, these DPUs run at 350 megahertz more recent generation runs at 425 megahertz. And as I said earlier, it's fine-grained multi-threaded. It can run up to 24 hardware threads, and the pipeline is with 14 stages. These dispatch, for thread selection, instruction fetch, register, operand read from the register file, operand formatting, operation in the ALU, or access to the WRAM, and finally result formatting. To understand how how fast this pipeline can be, we created a few micro benchmarks, or one micro benchmark with different versions to measure the arithmetic throughput for different data types and operations using a single DPU and changing the number of tasklets between 1 and 24 using different types of arithmetic operations, addition, subtraction, multiplication, and division, and different data types in 32, in 64, single precision floating point, and double. I'm going to show you some results here for the arithmetic throughput. As you can see in the y-axis, we have arithmetic throughput in mega operations per second, and in the x-axis, we have the tasklets, the spin threads that are called tasklets from 1 to 24. So these are some results for addition and subtraction of 32-bit integers. These are results for multiplication and division, and these are the results for the rest of the data types. As you can see, the one first observation here is that the arithmetic throughput in all cases saturates at 11 or more tasklets. And this number is related to the number of pipeline stages. It's an observation that is consistent for all data types and operations. However, the maximum throughput, the arithmetic throughput that we can achieve for different operations is not the same. You can already see that there is significant difference between addition and subtraction and multiplication and division, and also between integers and floating point numbers. The reason for that is that the DPUs, even though they are 32-bit processors, they don't have support for, they only have support for integer addition and subtraction, but not for multiplication and division, and not for floating point numbers. These are emulated by the runtime library, and this is what makes that they need many more execution cycles to execute, and basically the resulting arithmetic throughput is lower. In the paper, we also did some analysis about the access to the WRAM, to the scratchpad. Let's say, key conclusion here is that when the pipeline is full, you can access 8 bytes in one cycle. And but yeah, we tried different experiments as well that you can check in the paper. Yeah, more interesting are the results for the MRAM, the DRAM bank, and how what's the latency and what's the bandwidth of moving the data between the DRAM bank and the scratchpad. Because every time that we need to operate on one array residing in the DRAM bank, we need to move chunks of this array to the WRAM for the pipeline to access the data, to access the array elements from there. So that's our goal, understanding what's or measuring what's the latency and bandwidth to this memory. And for that, we created several micro benchmarks. In the first one, we just measured the latency of a single DMA transfer. There are 2 APIs for the DMA transfers. One is MRAM read for moving data from the MRAM to the WRAM, and the other one is MRAM write to move data from the WRAM to the MRAM. We also created benchmarks to measure the bandwidth. The first one is the stream benchmark with its 4 different versions: copy, add, scale, and triad. For copy, as you can see, we have 2 different versions. I will explain them in a few minutes. And we also have 2 versions of a strided access pattern that I will also explain, and random access pattern. But let's start with the latency measurements. So as you can see here in this figure, we have on the x-axis, or in these 2 plots, we have on the x-axis data transfer sizes between 8 bytes and 2048 bytes. That is a maximum one. And in the y-axis, we have bandwidth, megabytes per second, and latency in cycles. So we measure the cycles, but we also calculate the resulting MRAM bandwidth. And one first observation is that we can model the MRAM latency with a linear expression. as basically this expression on the slide, that as you can see, the thin black line matches pretty well the measurement, the actual measurements on the DPU. From more measurements, we inferred that beta is 0.5 cycles per byte, or 2 bytes per cycle, which basically means that the theoretical maximum MRAM bandwidth is 700 megabytes per second at 350 megahertz. So this is the one key observation here. First of all, the memory, the latency of access to the MRAM bank increases linearly with the transfer size, and that the maximum theoretical MRAM bandwidth is 2 bytes per cycle.
So this 2 byte per cycle is basically a circuit design limitation. You can only read a 2 byte.
Read only 2 bytes. No, the bus is the bus of the DMA engine is 64 bits. Yeah, that this is what results from activating one row and bringing the entire row of likely 2 kilobytes from the MRAM bank to the WRAM.
Well, I just try to understand why the bandwidth is 2 bytes.
Well, the bandwidth is 2 bytes.
Yeah.
Because that's what
The assumption.
Say again?
Is the assumption, or is some constraints you got from MRAM vendors, or where this 2 bytes come from?
We are inferring this from the measurements. I don't know exactly how internally the memory is being accessed.
Okay, but you got the MRAM chip?
Yes.
Memory?
Yeah, we measured this in the real chip. Yes.
This is bandwidth for one bank MRAM or for the whole MRAM?
No, that's for, well, the MRAM has one, it's just one bank. So inside each chip there are 8 banks, and each DPU has its own bank. So that's just one bank. So the overall, as I said here, and as you can see also on the plot, maximum bandwidth is, theoretical bandwidth is 700 megabytes per second. The aggregated bandwidth for the entire PIM system is like, in the most recent one is about 2 terabytes per second. Okay, so let's see also some results for the stream benchmark, because we also measured the bandwidth with the stream benchmark, and as you can already see, with very similar results, very close to 700 megabytes per second. As I said earlier, there are 2 versions of copy. The first one is called copy DMA, because in this one, we are just using the DMA transfers, the MRAM to WRAM transfer, and the WRAM to MRAM transfer. The DMA engine is able to only sustain one single transfer at a time, but you can see a little increase in the bandwidth when we go from 1 tasklet to 2 tasklets. That's simply because when you have 2 tasklets, there will always be a transfer ready to be issued, and that's why it results in a little bit higher bandwidth. So these are the results for copy DMA, these are the results for copy and for add, and these are the results for scale and triad. And there are something that you can observe here is that the saturation point of the different versions might be different, right? That we have copy DMA saturates with 2 tasklets, and copy and add saturate with 4 and 6 tasklets respectively, and scale and triad saturate at 11 tasklets. So these make us distinguish between memory-bound workloads and compute-bound workloads. In a memory-bound workload, and that will be the case of copy and add, the latency of accesses to the MRAM, or the latency of moving the data between the MRAM and the WRAM, is longer than the latency of the instructions that are being executed in the pipeline. For copy, for example, that makes a lot of sense because basically there is no computation, right? We are just copying data. For add, we are just doing one addition every 8 bytes or every 16 bytes that we read from from memory. So that's why in these cases, the execution in the pipeline takes shorter latency than accessing the MRAM band. However, in scale and triad, because these two use multiplication, and remember, multiplication is emulated, so it needs many more cycles. The multiplication needs more cycles, so in that case, the pipeline latency is hiding the MRAM access latency. So as you see, that's why the saturation point is at 11 tasklets, and that's what we call a compute-bound workload. As you can imagine as well, and as you can expect after seeing these results, most real workloads are going to be compute-bound on this architecture if they use streaming accesses, if they access large consecutive chunks of data from the MRAM. Most of the times they will be compute bound. Now let's take a look at the results for a strided access pattern and for random access pattern. Here we have for a strided access pattern, we have two different ways of doing these accesses. The first one is called coarse grain strided access, because we are moving a large chunk of data, for example, 1 kilobyte or 2 kilobytes from the MRAM to the WRAM, and then we perform the strided accesses in the WRAM directly. In the fine grain access, we are just accessing from MRAM the data that is really needed. So the strided access goes directly to MRAM and brings 8 bytes to the WRAM, and that's the data that is going to be used. For the random access pattern, because it's random, we just use fine grain approach. So let's take a look at the results. Observe that this is sustaining MRAM bandwidth over the stride and the x-axis. On the left-hand side, we have coarse grain strided access results. In the right-hand side, we have fine grain strided and random access. For the coarse grain strided access, you can see how the effective bandwidth reduces with the stride. That's something that makes sense because we are bringing a large chunk of data to the MRAM, to the WRAM, but only using a few, some elements of that data, right? And in the right-hand side, we see that the bandwidth, regardless of the stride, is always the same for the fine-grained access and for the fine-grained strided access and for the random access, because we are just using the smallest size transfer, which is 8 bytes, and bringing only the data that is needed. So we see a large difference in the maximum sustained bandwidth. We also see that at some point it makes more sense to start using the fine grain strided access than the coarse grain strided access, and that, according to our experiments, happens with a stride of 16 or larger. So yeah, those are the numbers for the effective bandwidth. And one programming recommendation that comes out of these experiments is that for strides that are smaller than 16 8-byte elements, it's better to fetch a contiguous chunk of data, bring it to the WRAM and access it, do the strided accesses in the WRAM. And if the strides are larger, then we can directly go to the MRAM and just bring the data that is really needed. Those would be the fine-grained strided accesses. We run some more experiments, some more micro-benchmark experiments for arithmetic throughput versus operational intensity. So what we do here is moving data from the MRAM to the WRAM, and then performing a variable number of operations on each element in the WRAM. That's how we change the operational intensity. So in that sense, this experiment is inspired by the roofline model. And that's more or less what we wanted to study here. These are some results. These are for 32-bit integer addition. So basically, as I said, we bring a large chunk of data to the WRAM, and then we go one by one over the elements of that chunk of data and performing, in this case, a variable number of additions from very low operational intensity, 1/2048 bytes. So that's just one addition every 2 kilobytes that we read, to a high operational intensity of 8 operations per byte. And the y-axis presents the arithmetic throughput. Each of the dots in the plot correspond to the different number of tasklets that we use in the experiment. We are experimenting here with 1 to 16 tasklets. And you can clearly see that there is a memory-bound region and there is a compute-bound region. In the memory-bound region, the arithmetic throughput increases with the operational intensity. And as you can see, the saturation point happens with a number of tasklets that is less than 11. And that's more or less in line with what we observed previously for string copy and add. On the right-hand side, in the compute-bound region, we see that the arithmetic throughput is flat at its maximum. And in this case, the saturation happens at 11 tasklets. We also observe here that the throughput saturation point, which is the operational intensity where we see the transition between the memory-bound region and the compute-bound region, is very low. And it's as low as 1/4 for the integral addition of 32-bit elements. And this is even worse for other data types and operations. So in general, what we can see is that the throughput, the arithmetic throughput of the DPU saturates at low or very low operational intensity. And the conclusion is that the DPU is fundamentally a compute-bound processor. So whenever we have streaming memory accesses, the workloads will be compute-bound. So what we expect is that workloads will be compute-bound, and hopefully workloads that work well for this architecture will be very memory-bound in processor-centric systems, in CPUs and in GPUs. But because we wanted to understand more about the workloads themselves, we created this suite of benchmarks that are, first of all, memory-bound on CPU, and then diverse in terms of application domain and in terms of characteristics. So we have, these are our goals to create a benchmark suite. As I said, different application domains, memory-bound workloads, and in total we have 14 different workloads and 16 different benchmarks. And this is a list of workloads where you can see vector addition, matrix vector multiplication, sparse matrix vector multiplication. There are a couple of database operators. There are other data analytics workloads like binary search or time series analysis. We also have graph processing, multi-layer perceptron, image processing, some parallel primitives as well. So it's a quite good variety of workloads. All of them have in common that they fall in the memory-bound area of the roofline. So they are memory-bound on the CPU that we use for this experiment. So in principle, they are good candidates for processing in memory. The workloads are also diverse in terms of domain, as you have seen in the previous slide, but also in terms of memory access pattern, operation and data type, and communication and synchronization needs. So let's see the evaluation for these workloads. We perform strong and weak scaling experiments and also comparison to CPU and GPU. First of all, we evaluate the 16 prim benchmarks on 2 UPMEM-based pin systems that you saw in the beginning of the talk. And we carry out the strong and weak scaling experiments on the larger pin system. 1 DPU with different number of tasklets. These are strong scaling experiments. 1 rank, strong and weak scaling experiments on 1 rank, and then an experiments, strong scaling experiments for up to 32 ranks. We also do a comparison of the UPMEM-based pin systems to a state-of-the-art CPUs and GPU. Here we use an Intel Xeon CPU and an NVIDIA Titan V GPU. So first of all, let me show you some results for a strong scaling on 1 DPU. Observe that here we set the number of tasklets to 1, 2, 4, 8, and 16. It's one single pin core or one single DPU. If you look closer at the plots, you will see that we are representing the DPU time, that is the execution of the kernel time itself, the kernel itself on the pin core. We have inter-DPU communication time, not in the case of a single DPU, but You can see it in the other experiments with more than one DPU. We have CPU to DPU data transfer time and DPU to CPU time. And finally, we also have the speed up of the kernel time over one task. So yeah, let's discuss some observations here. First of all is that we observe that for most of the workloads, the best performing number of tasklets is 16. And is 16 and not 11, because 11 is, remember, is a throughput saturation point. Is 16 and not 11 because we are testing 8 or 16 tasklets. So that's why the number of tasklets with the best performance is 16. And we see speed ups that are almost linear when we double the number of tasklets from 1 to 8, because we are filling the pipeline. After that, the throughput saturates with 11 tasklets, and that's why we don't see so much speed up from 8 to 16 tasklets. So all of this would make sense with the observations in the arithmetic and the micro benchmark analysis. The key observation is that number of tasklets greater than 11 is a good choice for more real world workloads. And that's because that number of tasklets fully utilizes the pipeline. So another observation is that for different workloads, so there are several of the workloads that don't use intra-DPU synchronization primitives. I didn't mention that earlier, but we are running threads, and these threads can synchronize in different ways. We can use barriers, handshakes, semaphores, and mutexes. So some of the workloads don't use synchronization primitives, so there is nothing to say about that. In some other cases, they use synchronization primitives, for example, one barrier eventually, or maybe handshakes in the case of the scan operations. But in this case, there is not much synchronization cost. The usage of the synchronization primitives is pretty lightweight. But in 3 of the workloads, we see that that there is much more contention when accessing shared data structures, in this case with mutexes. That happens for BFS, one of the versions of histogram, and one of the kernels in the transposition benchmark. So for example, for this version of the histogram, in the histogram, it's basically, in this version of the histogram, we are basically generating one subhistogram per DPU. So all tasklets need to update the same subhistogram. And they use mutexes to do that, right? They define a critical section with the mutexes, and only one of the tasklets can update the histogram at a time in order to have atomic updates. So the observation here is that the best performing number of tasklets is not 16 in this case, is 8, because when we increase the number of tasklets, there is more contention and the performance gets affected. So the intensive use of intra-DPU synchronization across tasklets may limit the scalability. That's the overall observation, or overall conclusion here. In the paper, you can check more results for one rank. For example, for one rank, in general, what we observe is that the kernel time, the DPU kernel time, reduces every time, the performance increases linearly when we increase the number of DPUs. In some cases, the execution is not, the scaling is not that ideal, especially because for some of the workloads, we see that we start observing important overhead or significant overhead from the inter-DPU synchronization. That's the case of BFS, for example, or Needleman-Bunch, or even the MLP. So because remember, there is no direct communication channel between different pin cores or DPUs, so all communication needs to go through the host, and in these cases, we see that this ends up affecting the performance. And can be even worse when we go farther in the number of DPUs. These are strong scaling experiments for up to 32 ranks, so up to 2048 DPUs. If you take a look at the workloads that I mentioned earlier, BFS, Needleman-Bunch, or MLP, you see that most of the time is spent on this inter-DPU communication. Obviously, these are not good candidates for good workloads, not suitable workloads for this pin system. However, we can see that in other cases, most of the cases, I would say, the performance keeps increasing as we increase the number of DPUs. In the paper, we also have weak scaling experiments for one rank. The observations are more or less along the lines of the ones that I already mentioned in the previous slides. And now let's take a look at the evaluation in comparison to CPU and GPU. As I mentioned earlier, we are comparing to an Intel Xeon CPU and an NVIDIA Titan 5 GPU. The baseline codes that we use are also available in our repository. One thing that I would like to mention here is that we are using only data sets, the largest data set that we can fit in the GPU memory. So in that sense, we are not exploiting the inherent advantage that the PIM system has because it has much larger memory. Remember that the larger PIM system has 160 gigabytes of memory that is more than, right, at least twice as much as the more recent GPUs from NVIDIA have. So we are not taking advantage of that advantage of the PIM system because we wanted to test, let's say, under fair conditions. So for performance comparison, observe that here we are showing a speed up over the CPU with a logarithmic scale, and we classified all 16 workloads in two main groups, depending on how well the larger PIM system performs in comparison to the GPU. So these are the more PIM suitable workloads, the less PIM suitable workloads, and these are the GMIN values. So some observations is that both PIM systems, the larger one and the smaller one, outperform the CPU in all cases, except three of the workloads, SPMB, BFS, and NW. For BFS and NW, you can already imagine what's the reason. We have already seen that for both inter-DPU communication is a big overhead. So that's a reason, basically that's the reason that kills the performance. In the case of SPMB, it's mostly because this version of SPMB uses floating point operands. And because floating point is emulated and it also uses multiplication. Yeah, it's not as is is not a good fit for these PIM systems. But overall, we see that both systems outperform the CPU for 13 of the PIM benchmarks with a speed up of 93 times for the larger PIM system. So in comparison to the GPU, we see that for 10 of the PIM benchmarks, the larger PIM system outperforms the GPU by an average of 2.54 times, and the smaller PIM system is within 65% the performance of the GPU. These 10 workloads have something in common. They have three main characteristics in common. The first one is that they use streaming memory accesses because that's the way of maximizing the bandwidth. The second the second characteristic is that they use no inter-DPU synchronization or very little inter-DPU synchronization. Some of them use inter-DPU synchronization, but the cost is clearly amortized. And the third characteristic is that there is no or little use of integer multiplication, integer division, or floating point operations. So with these three characteristics, we can say that a workload is potentially suitable to the UPMEM PIM system. In terms of energy comparison, unfortunately, we could only measure energy in the smaller PIM system, but well, overall, we can say that the observations are in line with the observations for performance. One key reason for that is that the PIM systems are more or less in the same ballpark of energy consumption than the CPU or the GPU. So wherever you see performance improvement, you can also see energy savings. And now let's conclude with some key takeaways. The first key takeaway, as you might remember, is that the throughput saturation point is pretty low. So key takeaway number one is that the UPMEM PIM architecture is fundamentally compute bound. So as a result, the most suitable workloads are memory bound in conventional processor-centric systems. And this observation, this compute boundedness of the PIM architecture is what results in the fact that we need to, the best performing number of tasklets is usually 11 or more. And that's something that we have observed also in later work. This slide corresponds to one of the papers that I presented this week at ISPAS. Is an analysis of machine learning training workloads, linear regression, logistic regression, decision tree, and k-means clustering. And as you can see, in all 4 cases and all different versions that we implemented, the saturation happens at 11 tasklets. Remember that this is because the architecture is compute bound. So in most, basically in all real workloads, the pipeline latency hides the memory latency. So the kernels are compute bound, and that's let's say one key takeaway of this work that I presented this week. And one recommendation is as well to keep the PIM cores, the DPUs fully busy by keeping their pipeline fully busy, because that's a way of maximizing the arithmetic throughput.
So when you say the pipeline fully busy, do you mean we need to improve the utilization of the PIM cores, or we need to provide sufficient large memory bandwidth to supply the data?
When I'm saying pipeline fully busy, I mean using enough number of threads.
Right.
So in each DPU, we can run up to 24 threads. And our observation is that after 11 tasklets, 11 threads, the best performance, the arithmetic throughput saturates. So that's basically what we are saying here.
Interesting.
Okay, so key takeaway number 2 is that the most well-suited workloads for the admin PIM architecture use no arithmetic operations or use only simple operations, for example, bitwise operations or integral addition and subtraction, because remember, multiplication, division, and floating point operations are emulated. Key takeaway number 3 is that the most well-suited workloads for this architecture require little or no communication across DPUs. Remember that this is also one characteristic of the most well-suited workloads. And as a final key takeaway, the comparison to CPU and GPU for 13 of the PRIM benchmarks, the larger PIM system outperformed the CPU that we compared to. Also for 10 of the PRIM benchmarks, it outperformed the GPU that we use in our analysis. And in terms of energy efficiency, we have similar observations. So we basically can save energy and with the workloads where we can provide performance improvements. As I said, we have continued working with this architecture, exploring even more different applications, machine learning training. In this study of machine learning training, we implemented logistic regression, linear regression, decision tree, and k-means. The first 2, linear and logistic regression, they require multiplication, and that's why they are not so well suited, because remember that the multiplication is emulated, but decision tree and k-means, they basically use comparisons and use addition, subtraction, so they are not so compute intensive in that sense. So they outperform the CPU and the GPU. In this work, we compared to an NVIDIA A100, and both decision tree and k-means are faster than the CPU and the GPU. In the case of decision tree, is 20 times faster than the CPU and 1.34 times faster than the GPU. This is for one data set, Higgs boson data set. For the PIM version of k-means, we observe 2.8 and 3.2 times performance improvement over the CPU and the GPU respectively. We also ran some experiments with a larger data set, the Criteo 1 terabyte data set for decision tree and k-means. In this case, the speed up of the PIM version of decision tree increases with respect to the previous data set, up to 62 times faster than the CPU and 4.5 times faster than the GPU. One main reason here for the additional speed up is that because the data set is larger, we can keep the PIM cores busy for longer time, and that's why the maximum number of PIM cores available, remember 2,500 PIM cores, produce the best performance in the case of the Criteo dataset and decision tree. For the previous dataset, the maximum performance was not with the maximum number of DPUs because the dataset was relatively small. And in the case of K-means, we observe similar speedups for Criteo as we observe for the Higgs boson. So key takeaway from this work is that machine learning workloads that require mainly operations natively supported by the PIM architecture, as is the case of decision tree and K-means clustering, outperform their CPU and GPU counterparts. And to conclude, again, the executive summary, I'm not going to repeat it completely. Basically, ABMEM has made public and commercializes the first real-world PIM architecture that is based on DDR4 chips with small processors called DRAM processing units. In our work, we have analyzed this architecture. We have performed a benchmarking and workload suitability study, and we came up with several observations, takeaways, and recommendations related to our characterization of this architecture and the different workloads that we implemented that are all together in the PIM benchmark suite that is publicly available. As I mentioned as well in the beginning, there is a short version of the paper, a long version of the paper, all available in archive, and the repository is also public. Of course, the code is open source. We have delivered several talks and lectures about this architecture. This is just one example that was almost 3 hours explaining all the different details of the architecture with a lot of discussion as well and many good questions. And after that, we have continued working on understanding more about this architecture and what are suitable workloads and how to implement workloads here to maximize the performance. This is one study that we presented last year at Sigmetrics, where we implemented 25 different versions of sparse matrix vector multiplication with comparison to CPU and GPU as well. Sparse matrix vector multiplication is not an ideal fit for this PIM system, but still, I think that the most interesting outcome of this work is that the gap between compute and memory is close with respect to CPU and GPU. Basically, what I'm saying is that in the PIM system, we are able to exploit a higher fraction of the peak performance of the peak arithmetic throughput than on the CPU and the GPU, much more indeed. This is the paper, one of the papers that I presented at ISPAS, the machine learning training analysis. This is another one recently published at the Bioinformatics Journal. It's a framework for high throughput sequence alignment, where we implemented Smith-Waterman, Needleman-Bunch, GNASM, and the wavefront algorithm that is the state-of-the-art in sequence alignment for bioinformatics. This is the second paper that I presented at ISPAS, is a library for efficient transcendental functions. Transcendental functions are obviously not supported by this architecture, but they can be useful in many workloads, also in workloads that are memory bound in CPUs and GPUs, activation functions in machine learning workloads, for example. So here we explore different methods to implement transcendental functions in software, core-dig-based or lookup table-based. If you are interested in learning more about real PIM architectures, this is one. Here you have some links to the tutorial that we organized at HPCA this year. We repeated it later at ASPLOS, and we are going to have it again in ISPA. ISCA. No. There will be new contents for sure, new lectures, and also new invited talks. We have had talks from in the previous ones. We have had talks from people from IBM, from SK Hynix, from Alibaba as well, from other universities, like for example, the Professor Fedorova and from the University of British Columbia. So yeah, in the end, very interesting experience for us as well. A way of condensing and putting all together what we have been teaching already for several semesters in our processing in memory course. And I'll give you here also the links to the materials. So this is all from my side. So now if you have any other questions, please let me know. I'll be glad to answer and continue with the discussion.
Okay, any questions?
I was curious about the inter-DPU communication. So currently, whether those DPU are within the same rank or different rank, they all have to go through the CPU for communication, right?
Yeah.
So, so the first question is about this. So, what is the coherence model for this PIM-enabled DRAMs? Is it like we have to pin this memory and tag them as uncacheable before we do any computation, or they can be accessed in some certain mechanisms?
So coherence is here is completely managed by the programmer. And let's say that one thing that simplifies everything is that the CPU cannot access the MRAM banks while the DPUs are working. So that let's say that the CPU access is blocked. So in that sense, you don't have to worry about the CPU. And then it's the responsibility of the programmer to move data, to move results back from the WRAM to the MRAM, and then to bring to the CPU, to the main memory, whatever data is going to be needed by the CPU later. So in the end, there is no need for coherence other than what the programmer can do by herself.
So whatever the CPU is able to process, they have to stay in the main memory, right?
Yes, exactly. So the CPU after the kernel finishes the execution, the banks become available to the CPU again. The CPU can read data from there, but needs to move it to the main memory and then use the data.
And the second question is when a DPU access either its own banks or other banks, is it directly using the physical address or?
Yes, they are directly using physical addresses. Yes,
So
there is no.
Those PIM enabled DIM is like a special. It is not within the same system memory space, but it's like a special memory space.
Yeah, kind of. Yes.
Thank you.
Thank you for the question. I think there is one question in Zoom.
Yeah, there's one question online.
Yes. Is there any performance comparison of DPUs with SRAM-based PIN systems? That's a good question. No, I don't have any comparison like that. I don't have access to any SRAM-based PIN system. I would be glad to evaluate those kind of systems as well and compare for these type of workloads. Yeah. I think that SRAM-based PIN systems might be a little bit more specialized in the type of workloads that they support, compared to this one that in principle is general purpose. You can program basically whatever you want, even though performance might not be great in all cases. Thank you for the question.
Okay, thanks.
Any other questions? Yes.
So what would your comment be on ENVM based DRAMs?
MVM for PIM compared to DRAM. I mean, I think that the research, the research and the developments that are being done in processing in memory using MVMs is different from this kind of work. It's what we can call processing using memory, because the computation is being done by the memory cells themselves. It's also, I think, pretty specialized computation, basically exploiting Kirchhoff laws to perform matrix vector multiplication or dot product operations, basically. So in that sense, it's different from this. It's not that different from other, like, for example, the SRAM-based PIM or DRAM-based PIM or processing using DRAM that in our group we are also working on. Not that different, because in those cases, it's also taking advantage of the analog capability of the analog operations of the memory cells. I think that both approaches, regardless of what's the memory technology in particular, both approaches can be complementary. We published, I think it was in Micro 2021, we published indeed one paper where we used both kind of things for graph matching problems. In some cases, you can use processing using DRAM to perform simple operations using the memory cells. Like, for example, AND operations for intersections in graph matching problems. And then in some other cases, it might not be so beneficial to use that. And in that case, it might be better to use something like a more general purpose near memory processing core. So I think that we'll have to see, but both are pretty promising directions. Processing using memory is a little bit more far-fetched, in my opinion. This is already there. It's real. You can use it. You can buy it and start doing processing in memory.
I think about time, so let's conclude this section. Yes, thank you everyone who attended this meeting in person or online.
Okay, yeah. Thank you, everyone.
We can bring the people back to the slide.